Okay, still working on learning target 5.2, finding 6 trig functions using triangles, okay? So far we've kind of just given you any sorts of random size triangles, okay? But there were a couple special triangles that you used a lot in geometry, okay? They were the 30-60-90 triangle and the 45-45-90 triangle. Some of you maybe have still remembered them just a little bit, but if not, we're going to show you with trig here a little bit, or really not necessarily with trig, but we're using geometry to do it. But we're going to show you why those triangles are the way they are, and then you're going to use these triangles quite a bit, okay? Especially with all of your trig functions, sine, cosine, tangent, okay? Now, we're going to be deriving these triangles, okay? We're going to derive the relationship of the sides, okay? And this is a test question. Okay, this is definitely a test question, so you'll want to be able to write this stuff down when I ask you this on a test, all right? We'll start with the 45-45-90 relationship. So we're going to derive the 45-45-90 triangle. Okay? And that's going to be your directions on the test. Derive the 45-45-90 triangle, or derive the 30-60-90 triangle, okay? So first of all, let's just draw a 45-45-90 triangle. All right, do your best. Alright, I'm not going to give you any lengths on here, alright, but what do you definitely know about some of the lengths of the sides on that triangle?
That the adjacent, it would be the, not the hypotenuse, but the other two
The
sides
legs?
are the same.
Yep, the legs have to be the same, right? Because opposite a 45-degree angle and opposite a 45-degree angle, if the angles are the same, the sides opposite them are the same. It's an isosceles triangle is what it is. So we'll call those x, yeah.
And would the hypotenuse be twice the amount of the legs?
Not quite.
Wait, no, it'd be the,
It'd be this twice the square root.
yeah, twice the square root of 2 times.
Root 2 times that. You
Yeah.
remember that from geometry,
Yep.
okay? But here's your deriving part of it, okay? Not just having to memorize it, you can actually derive it and figure it out in case you forget, okay? We know these sides have to be the same, so let's call them x. We don't know this length right now. Well, if you know 2 sides of a right triangle, you can figure out the third side by using Pythagorean's theorem, right? So I would go,
X squared.
if we call this c for right now, all right, x squared plus x squared equals c squared, correct?
Yeah.
And we want to figure out what c is equal to. So let's solve this equation simply now for c. X squared plus x squared is
X squared.
2x squared,
2x squared.
okay?
I'm off today.
And now if you're solving for c, what do you need to do to get rid of the squared? Square root both sides. Okay? The square root of c squared, that is your c right there. The square root of 2x squared, we kind of were taught to break that down. 2 times x. So what can you bring out to the front of the radical?
X.
And x, the 2 stays on the inside, and what do you get? X root 2. So your c value right there is x root 2. So your hypotenuse, like you guys said, because you remembered from geometry, which is very good, okay? The length of that hypotenuse is x root 2. So this right here would be the work that I'm looking for, along with the picture. You need the picture to go with it so we know what the heck you're talking about, okay? All right? But this is the work that I'd be looking for on that test question, okay? You're showing me how we're getting x root 2. You don't need to tell me why these are both x, all right? You don't need to tell me that at all, all right? We're going to assume you know that across in the same angles will be the same length of sides on a triangle, okay? But use Pythagorean's theorem to derive the length of that hypotenuse. Questions on that, Jake?
Could you like plug in a number for x to figure out what c would be?
You could, but I want, for the deriving part, I want you to use x's. Okay, you absolutely could, but for the deriving part, I would like you to use x's because then that's showing it works for any size triangle, not just that specific number that you're referring to. But does that make sense?
Yeah.
Okay. All right, good. So there's your 45, 45, 90 triangle. Your assignment is going to be to find all of the 6 trig functions of a 45-degree angle. I'll do one with you, you can do the other 5, it's pretty easy, okay? So the sine of a 45-degree angle then, the sine of any 45-degree angle, whether the triangle's small or the triangle's big, the sine of a 45-degree angle is going to equal what over what?
X over
X over x root 2. X's cancel out. So now I have 1 over root 2. Can't leave a radical in your denominator.
So it's just root 2 over 2.
Root 2 over 2. Okay? So the sine of any 45-degree angle is always going to equal root 2 over 2. And then, as part of your homework, what I might do, guys, is I might, in one area in your notebook, do all, basically 18 of them, because we're going to do, for 45s, do sine 45, cosine 45, tangent 45, cosecant 45, secant 45, cotangent 45, kind of get all them in a nice organized, column in your notebook, and then do the 30s and then do the 60s. That's what I might do. That way you have something always to reference back to look to. It's kind of like a nice chart to refer to, because we're going to use these angles a whole bunch here in the next few weeks, even probably a month. Okay, we're using this stuff a lot, so. But definitely you'll do this one, then cosine, and so on. You kind of follow what I'm saying there?
Yeah.
Okay, I'm not going to do any more. I think you kind of got that. I'm going to go to the 30, 60, 90. All right? Okay, derive a 30, 60, 90 triangle. To derive this triangle, I'm actually going to start with an equilateral triangle. Okay? To the best of my ability, that is an equilateral triangle. I'm going to label
Every side 60.
all the angles are 60. And we know all the sides are the same, and you'll see why in a little bit. I'm going to label all the sides 2x. Not just x, I'm going to label them all 2x. You could label them all x. You'll see why it makes it a little bit annoying here in a second. But I'm going to start with 2x. Okay? So, nothing. Could that represent every equilateral triangle in the world? Could it?
Sure.
Sure, because x could be anything, right? X could be a tiny decimal, x could be a million, we don't know. All right? That could represent every single equilateral, so it's true for all equilateral triangles. Okay? Now, I'm going to take this, and I'm going to cut it right down the middle like this. Okay? I'm going to bisect that top angle. So now, if I look at just one of those,
Yeah, 30, 60, 90.
if I look at the one here on the left, I don't know why I chose the left one, I could have chosen the right one, doesn't matter. But I've created what type of triangle?
30, 60, 90.
30, 60, 90. The 60 would be down here, the 30 would be right here. Okay?
See what I can
Do we know the lengths of any sides?
Hypotenuse and the base.
This was 2x, right? Okay? The bottom would be x, and that's why I chose to make that 2x, because then I don't have to deal with the fraction here. Because if I called this x, I'd have to call this x over 2, or half x, and then I got to deal with halves. Okay? So now this is just x right here. So this is 2x, this is x, because when you bisect an angle from the top there on an isosceles or equilateral triangle, you're also cutting the bottom exactly in half too. It was 2x units long, now it's just x units long. Okay? Well, now let's figure out that third side. How are we going to do it?
Pythagorean
Pythagorean theorem. For our case, let's call that our b for right now, okay? So x squared plus b squared equals 2x squared. I'm just writing that out. If you want to square it yourself already and make it 4x squared, that's fine, but I'm just writing that out for our sake here, okay? Everybody knows where I'm getting that. X squared plus b squared equals 4x squared, because 2x times 2x is 4x squared. Okay, now I'm solving for b, so what do I need to do next?
Subtract x squared.
Subtract 1x squared from both sides. Subtract 1x squared, subtract 1x squared, so b squared is equal to what?
3x squared.
3x squared, good job. Okay, next thing we do?
Square root of the b squared.
Yep, square root to both sides of it to get b by itself. So b would equal the square root of 3 times x, if you like to break that down, or however you guys simplify radicals. You
X
can
square root of 3.
bring the x out front, because there's 2 of them in there. So b equals x root 3. So your 30, 60, 90 triangle, the side across from the 30 is x, the side across from the 60 is x root 3, and the hypotenuse is always twice the little side, or twice this side right here. So you got x, x root 3, and 2x. X, x root 3, and 2x. Okay? How do you remember them? Okay? Well, the smallest angle is the 30-degree angle, correct? Across from the smallest angle has to be the smallest side. And 1x is smaller than 2x. 1x is also smaller than root 3x, okay, because root 3 is more than 1, okay? The hypotenuse is always double the small side, so if you know the small side across from the 30, you just double it to get your hypotenuse. Okay, and if you know your small side, you just take that small side and multiply it by root 3 to get the side across from the 60. Okay? But again, for your purpose and your short little assignment, okay, all you guys are going to do is you're going to do the sine of 30 degrees equals the cosine of 30 degrees equals the sine of 60 degrees equals, and so on, okay, all the way, and do all 6 of them. Okay? Using your triangle, the sine of a 30-degree angle, if you go opposite over hypotenuse, you get x over 2x, right? If you look at your 30-degree and you go opposite over hypotenuse, you get x over 2x, which would reduce to what?
1/2.
1/2. Remember that from our little activity the other day too, how the sine of 30 degrees was 1/2? Okay? The ratio was 1 over 2 all the time. Okay, so the sine of 30 degrees will always be 1/2. Okay? The cosine of 30 degrees, if you go adjacent over hypotenuse, what would that be?
X root 3 over 2x.
X root 3 over 2x, and that would simplify to simply just what?
Root 3 over 2.
Root 3 over 2, yep, very good. Root 3 over 2, so we're getting a few more of them done. You'll do tangent, you'll do cosecant, you'll do secant, you'll do cotangent, do all 6 of them for the 30, and then we'll do all 6 of them for the 60 as well. As long as let's do one for the 60, so I've done one for each one. Sine of 60, what would sine of 60 be? Opposite over hypotenuse for 60.
Wouldn't it be the same?
Wouldn't be cosine 30 the same as
Same as cosine 30? You're right. So the sine of 60 equals root 3 over 2. Okay? Now maybe as you're doing your work, you're going to write it out this way, okay? If you want to make a nice chart with all 18 answers or something somewhere, maybe you don't want to have all that work shown in between there, but that's entirely up to you. We also will make a nice chart with even more angles eventually, so maybe you won't even need that. But your assignment, guys, is simply 18 problems, okay? And we've done about 4 of them already. You're going to do sine 30, cosine 30, tangent 30. Does everybody understand how I'm explaining the assignment?
Yeah.
So you'll have 6 problems with a 30-degree angle, 6 problems with a 60-degree angle, and then if I go back, 6 problems with the 45-degree angle. Those are your 18 problems, just get those finished up, okay? Because these problems are also on the test. So like if I ask you on the test, find for me the cosine of 30 degrees. Well, you'd want to be able to draw the triangle and then find the cosine of 30 degrees. Okay? You will also have to derive one of the two triangles too. You'll either derive the 45, 45, 91 like we did here in your notes, or you'll have to derive the 30, 60, 91. Be prepared for both.
I'm calling 30, 60.
Okay? Any questions?